12.1a, we're going to check conditions for performing an inference about the slope of the population regression line. Let's look at this example here. Many people believe that students learn better if they sit closer to the front of the classroom. Does sitting closer cause higher achievement, or do better students simply choose to sit in the front? To investigate, an AP Stats teacher randomly assigned students to seat locations in his classroom for a particular chapter and recorded the test scores for each student at the end of the chapter. The explanatory variable in this experiment, which row the students were assigned, row 1 to the closest to the front and row 7 the furthest away. Here are the results, including a scatter plot and least squares regression line. So what we have here is the corresponding rows students sat in and the scores with that. So therefore, this individual actually plotted the 30 various ordered pairs that go with this data. For example, row 1, a score of 76, row 1, a score of 77. You're going to see right here, and all the other scatter plots. So the intention to do this is to see, is there a linear relationship between the row you're sitting in and your scoring the test? We can also see here that a least squares regression line was actually figured out. I'm going to put score hat, by the way, because it is our prediction. So the predicted score is going to be 86 minus 1.12 times the row you're in. Remember R squared from chapter 3. This is called the coefficient of determination. So in part A, let's interpret the slope of the least squares regression line in this context. The slope here is going to be the negative 1.12. And what that means, remember in context, is this. For each additional row a student sits from the front, their predicted score will decrease by 1.12 points. Now let's interpret the y-intercept. The y-intercept in this case is going to be the 86. And what that means is the score of a student that sits in row 0 would actually be 86 points. But folks, that makes no sense. The first row that actually is created is row 1. So in context, the y-intercept for this particular problem is not relevant. Letter C is a great review question also. Here they want us to interpret R of the least squares regression line and do this in context. Whenever they want you to explain R for bivariate data, that means your DOFs. Remember, direction, form, strength, and any possible outliers. Now, R was not recorded, but R squared was. So what we can do is take R squared and take the square root of that. If we take the square root of that, we get 0.217. Now be careful. Remember, R, or correlation, is only for lines, by the way, and it goes from -1 to 1. So we need to figure out if this is going to be positive or negative. The way we can look at that is to reference the slope of the line. The slope of the line was negative, so technically we need to adjust our correlation to be a negative 0.217. Now we can definitely talk about the DOFs for that. The DOFs would be that the negative is going to cause it to have a negative relationship. It's not that strong because it's a little bit closer to 0, which means that there's no linear relationship. So it's really going to be somewhat of a weak linear relationship. So the best way to DOFs is to say it's technically a very weak, negative, somewhat linear relationship. Moving on to D, interpret R squared. Now R squared is this, again, and it's called the coefficient of determination. There's a standard definition that you want to use for R squared every single time, and I will guarantee you that you will see a question somewhere on your real AP exam with R squared. I see them every year. So in this case, R squared would be 4.7%. What does that mean? It means this. 4.7% of the variation in our student scores, which was our response variable, can be explained by this least squares regression line. That is not a lot of variation that can be explained. It means there's over 95% of the variation in this line is going to be explained by other variables. Technically, there's probably a better explanatory variable for student scores than the row that we're seeing. In letter E, is this a strong model? This does not seem to be a strong model at all. Remember that we definitely want to look at the scatter plot for that to see if it looks somewhat linear. We also want to look at the correlations and the coefficient of determination. Another thing we did do back in chapter 3 is we did graph the residual plot for this, but we're not going to cover that quite yet. And then letter F, is this an appropriate model? Well, it's not a strong model, but is it appropriate? For this case, it's probably not the most appropriate model. In some of the reasonings for that, the weak correlation, the low coefficient of determination. Question 2, great review of Chapter 4. Explain why it's important to randomly assign the students to seats rather than letting each student choose his or her own seat. Remember what the randomization, when you set up an experiment, is going to actually cause. In this case, if students are allowed to choose their own seats, the most conscientious students might choose to sit in the front, making it appear that sitting in the front causes higher scores. If we randomly assign the seats, the ability levels of students should be approximately the same in each row. And when you do the randomization in your experiment, that's how you control for the other lurking variables that you cannot control for. Number 3, does this negative slope provide convincing evidence that sitting closer causes higher achievement? Or is it plausible that the association is due to chance, variation, and just the random assignment itself? Now in this case, do remember an experiment was set up so a treatment was imposed. When you impose a treatment, you are allowed to make cause and effect assumptions about your particular study. But what they're going to recommend here is let's go ahead and do a simulation to see if this was just by random chance alone or not. Now let's just talk through how we could simulate the situation. So we had 30 students, so let's have 30 note cards of the exact same size and label each one with one of the students' scores. So record all of the scores that we saw in our actual sample that we took. Now shuffle the 30 cards and divide them into 7 piles. Now do look carefully. Rows 1, 2, 3, 6, and 7 had 4 people, whereas rows 5 and 6 actually had 5. So then you would lay them out accordingly. Based on that, we would then calculate the slope of the least squared regression line using that actual data. Basically, we would go through as we lay these cards out. Again, for row 1, for example, we would lay out the 4 cards that would show up. And then what we would want to do is actually plot all 4 of these ordered pairs, do the same thing for row 2, row 3, and so forth. That would give us a nice scatter plot. We could then, like it says here, actually compute a least squares regression line. Remember, all we would do for that is we would do hit our stat button, and we would calculate. On that one, we would do a linear regression. And that would give us the equation, and we would get a corresponding equation with that. Now, this would be one trial, and we'd get the actual equation, and then from there we could plot one dot that represents the slope from that equation. We would then repeat this process over and over again as many times to get a sampling distribution of our slope. And if we do that, here's what a possible distribution could look like. So this could be a possible sampling distribution of computing the slope many, many times and doing many, many simulations of our 30 students. So then part D of this wants to know, was our observed slope of negative 1.12 unusual, or is it possible to get a slope this small due to chance variation and random assignment? Let's see what conclusion we can make. Well, if we look at where the slope would be, it would be somewhere in here. So of all these 100 trials that we see, it looks like possibly there could be about 10 out of 100 that have the slope less than negative 1.12 or even more extreme. So we're talking about 10% chance. Now, would we consider that unusual or not? Think about our p-values. Typically, our alphas are set at 0.05 for our level of significance. So based on that, it's really not that unusual. So ultimately, what we could say is this study really does not give us convincing evidence that it makes a difference sitting closer to the class on one's grade performance for a test in this class. Let's talk about the formal process of analyzing 2 quantitative variables in the format of a scatter plot. And what that is looking at this, the population regression line. Remember, the population regression line would be the least squares regression line for the population of data. Our sample regression line is what we just took back on our last investigation. We did that sample 100 times and recorded all of the information that we got for our equations. And that sample regression line is what we saw back in chapter 3. It's our y hat equals our y-intercept plus the slope times x, where x is our explanatory variable and y is our response variable, just for that one sample of data. This right here are 3 different examples of when we were looking at Dr. Stearns and his family went to Old Faithful to look at the different eruption patterns for when the next one would go off. And basically all they're saying is they took various samples of one here, they took another sample and another sample, and they all give us slightly different linear regression lines because they are samples and they all have their own variability. Now, we did look at the sampling distributions as we were analyzing the different row that you sit in your test scores. Here is an actual sampling distribution related to a different type of scenario. Let's talk about the shape, center, and spread, or the SOCs of the sampling distribution. Keep in mind what a sampling distribution is. It is just taking many SRSs of the size n from a population and doing a regression and recording the slope. We saw that again for our test scores. If we look at the shape of the sampling distribution of all of these different slopes from various least squares regression line samples, we can clearly see that the shape is roughly symmetric and unimodal. The center of it actually looks like it is really close to our population slope, and the actual spread of it is close to the population standard deviation. One thing I want to highlight is notation. When we write the sample, remember the line was y hat equals a plus b x. Where in this, because it's from a sample, the a and the b are the sample y-intercept and the sample slope. Now we do want to compare it to the population. So notation for populations basically are going to go from our normal alphabet letters to the Greek characters. That's how you can really tell the difference a lot of the times between sample notation and population notation. But just make note here, for the population, we don't use A and B. Instead, for the y-intercept, we use alpha, and for the slope, we use the capital letter called beta. Now, I will tell you, obviously this is our last chapter, and this one has its very own unique conditions that must be checked. It's different from random, independence, and normalcy. So there's a acronym you can use to remember the conditions to check for a least squares regression analysis. And what I'm going to tell you it's the word liner. It's L-I-N-E-R. Not linear, but liner. It's a great way to help you remember that there are 5 conditions to check for this. The first one for L is linear. And what you're trying to see is does a linear relationship exist between x and y? The only way to look at this is to make a scatter plot. You also want to analyze the residual plot, and remember, look for no patterns in that the residual plot is centered around 0. So for just this one condition alone, we need a scatter plot and a residual plot to make our conclusions if that's met. I is going to be what we are used to is independence. So to test for independence or to check for it, all we have to do is think about this again. How were the data produced? Was it random sampling or random assignment? So if remember that they're doing an experiment setup, the independence has already been established. However, if they are sampling without replacement, you must check that 10% condition. And just remember, is our population greater than or equal to 10 times our sample size? So this here is really one condition that we see throughout the entire book. The third condition to check is actually going to be normalcy. So one that we're used to also looking at. What it means in this case, though, is we need to either make a stem plot, a histogram, or a normal plot of the residuals, and check for skewness or other departures. So I would recommend either plotting a stem plot or a histogram of the residuals and see if there's skewness or departures from that. Again, we've talked about normalcy as a condition within most of our tests and confidence intervals, but do be careful. This one is a little unique in that we're looking at the residuals. So you might have to kind of memorize this one a little more. The fourth condition deals with the letter E, and what you're looking for here is that there is equal variance. What that means is that the standard deviation of y is the same for all values of x. you're looking for the amount of scatter above and below the residuals at 0, and you're really looking for roughly the same from the smallest to the largest x value. Basically, you're going to look at the residual plot and see that the same amount of scatter, if we look at the x's as starting right here and the x's moving to here, we see the same amount of scatter. We don't see a little bit of scatter and then a lot of scatter like a funnel. And then the last one is R, which is also going to stand for our good old randomness that we're used to. So really, that random independent normalcy is seen in these 5 conditions. Here for randomness, were the data produced by random sampling or a random experiment. So technically, I would say there's really 2 more new conditions you have to check with a linear regression, which would be the L and the E components. Here's some more information about, the row that I sat in for my test and my test score. We already saw the scatter plot. We saw the least squares regression line, which again shows up right down here. Now they have some additional information for us. They did do a residual plot of all of the individuals for this. We also see a histogram of the actual frequency of the various residuals. So they looked at the residuals and then they plotted the frequency of that so we can look for the shape. Here's also a plot of the residuals in a normal probability plot. Now I will tell you, I have yet to see on an actual free response question where they require you to come up with all of this data for a Chapter 12 type of problem. Most times what I've seen is they have given you all of this information and they ask you to either check the conditions or if they ask you if it's an appropriate type of model. So don't worry about having to come up with all of this information, but know how to analyze it. So let's check the conditions. Remember for liner, the first is a linear scatter plot. You need to look at the scatter plot and the residual plot and look for a linear pattern. So look in your note packet, what do you notice about the scatter plot? What you could say for linear is that the scatter plot shows a weak linear relationship. Basically, it's DOFs. The residual plot does not show any obvious leftover patterns indicating the condition has been violated. So overall, what it's saying here is it does not show any obvious pattern. Remember, in the residual, we don't want a funnel shape. We don't want it to make a U shape. We just want to see random scatter throughout. So we're okay that this condition has not been violated for linear. Now for independence, which is I, the students were randomly assigned to seats and were monitored for cheating. Knowing the score for one student should not give information about another student's score. Independence condition is fine. Now let's check for the N, which is the normalcy. If we look at for normal, the histogram is roughly unimodal and symmetric. Also, the normal probability plot is making roughly a linear line. Now, you wouldn't have to look at both of these, but just one of them. But based on that, we could assume approximately normal. Then the E is going to be, is there equal variance? So for equal variance, there's a different amount of variability in each row. Differences aren't very large, and there is no symmetric pattern, such as increasing variability as X increases. Folks, what this means right here for this one is just look at that residual plot. So if you look at down here, I brought the plot in. What that means, there's a different amount of variability in each row. So if we look at row 1, we see high variability and low. If we look in row 2, we have low and high. 3, low, a low and a high. We're kind of seeing the equal distance in the scatter. It's not exactly the same, but for every X element, we're seeing that both or all of the X elements have a nice amount of equal variance happening amongst the residuals. And then R for our last component, the students were randomly assigned to their seats, so we're covered in that. That's how you check for the 5 conditions.